Okay, good morning and welcome this SCANVAC webinar. So we have today the topic of utilization of AI technologies in HVAC applications, and maybe for the short introduction I can say that this application of artificial intelligence has become widespread in various areas. This technology can bring many benefits and its uses and application possibilities are diverse. Some of the potential benefits are, for example, in the design, modeling, project management, and predictive maintenance, and system performance analysis. The use of artificial intelligence in the construction sector have become significantly more common in recent years, although this sector has been traditionally quite slow to adapt new technologies compared for other technical areas. We have seen nowadays technologies based on the language models and data analytics, and in this SCANVAC webinar we will present some of the potential application areas where artificial intelligence has been utilizing in construction and building service sector. So we have here webinar, and I remind you that all the presentation will be recorded, and if those want to listen that later, is available after a couple of days in SCANVAC webpage. Then other thing to remind you that you can ask the questions and put comments in the question and answer chat, and after this presentation we will go through them. And I will ask the questions for the speakers. So I will introduce for the who are our speakers today, and I forgot to present myself. My name is Risto Kosonen. I'm coming from Aalto University, and at the moment I'm SCANVAC president. But we have first speaker is Mikk Maivel from RH Technologies from Estonia. And Mikk has long experience in the real estate sector, including building service engineering and management, and he has worked a long time on the energy efficient and building automation areas. And he will now today talk about data-driven optimization layer of existing building management system, challenges and obstacles. The second speaker is coming from Sweden, from KTH, Royal Institute of Technology, Qian Wang, and he has long experience for research side for both industry-driven and theoretical research and development experience in the area of building installation technology, smart building and digital solution in building environment. And the third speaker is coming from consulting engineering company Granlund, Finland, Davor Stelja. He is AI lead and he has worked on bridging research and industry together and focusing on time series forecasting and control for HVAC and energy and anomaly detections in different systems. So we have speakers from background for real estate side, research orientated, and then we have consulting engineer side. So once more time, end of this session, we have time for the questions, and we will closing this session latest 10:30. So now, please, Mikk, screen is yours, and you can start with your talk. Thank you from my side.
Okay, perfect. Now I'm ready. Thank you for the introduction. And so, yeah, today I will give you an overview about RH Technology company and how we are using AI in existing building control. So how we are making existing buildings smart than they are. So we are focusing for commercial buildings and the buildings where have already BMS building management system available. And our software, RATech is a software company, and this software works on the top of the BMS to achieve the desired indoor climate with minimal cost. That's our main motto: desired indoor climate with minimal cost. Okay. About agenda, so I do have only 20 minutes, so I will give an overview what and how we are doing. Then some smart control examples. So it means how we are different compared with the BMS, and what additionally we are adding to the BMS system, and short summary as well. RA Technologies is actually founded 9 years ago. I have been working there 3.5 years now, and now I can say we are international company. We have experienced with buildings over 15 countries in different regions, mostly in Europe. But we have experienced a couple of buildings in Japan as well. In our company nowadays, it's almost more than 60 people who are working in RATech. I can say that approximately 1/3 of them have an HVAC background, and 1/3 have IT background, IT and controlling background, and 1/3 is more like sales and other supportive stuff. But let's move to what we are doing. So I will switch my pointer as well, then it's easier to follow. It's not very easy to understand that graph, but basically we need a building with HVAC systems that are connected to the BMS. And what we are adding data which is not usually taken into the BMS. For example, I haven't actually seen a building management system that uses electricity prices, electricity stock prices in the control. There are some products like heat pumps that are using electricity prices, but the pure or regular PMS that is controlling, for example, shopping mall, they are not using electricity stock prices in their control. So we are adding electricity prices. Then power grid balance service is actually at the moment available only in Estonia, but we hope to offer this service in Scandinavian countries as well soon. Besides that, we are adding weather forecast, and we are adding occupancy. Occupancy is very important because usually HVAC is designed for static conditions, and occupancy is very important. And a little bit later, I will show what kind of data sources we are using for taking occupancy, for using the occupancy. So after, we are taking all the necessary input data. So from the BMS, we are first while we start, we are adding our own category variable for all digital and analog input-output values for the BMS. It means for all the sensor values or the valve positions or the switches, and we are connecting them to our software. So it's partly automated, it's partly manual work. And after that, after the connection is made, so basically we made a digital twin of the building. And we group all the points to different components. It means one component is one air handling system, the second one is room, then is circuit, heating circuit, and its sub-circuits, and the same for the cooling side as well. And we made the connections between them. So the room is connected with a ventilation system that is serving that room, and also the room is connected to heating sub-circuit and cooling sub-circuit. After the connection is made, we are collecting data, we're analyzing, and we are doing a fault detection. Fault detection is a little bit different than the BMS is doing. BMS is usually doing a more alarm-based fault detection, but we are doing data-based fault detection. Performance insights during the control, we are checking and analyzing consumption data, and we are preparing different reports, usually monthly reports, annual reports, and so on. And during the control, we are doing 24/7 optimization, and if necessary, we are overwriting the setting values in BMS. It means we are using the same setting values what regular maintenance is using, so different set points, etc., etc. So one maybe an important thing is still everybody knows EPBD standards. EPBD is first launched more than 20 years ago, and quite soon there will be building automation and control system should be mandatory. I can say that, to be honest, typical or regular BMS usually won't fulfill the requirements, but so in our console we are adding this extra smart layer, and where we are continuously monitoring, doing our own fault detection, analysis, and active communication as well. One slide about faults. All the buildings which have BMS have their own BMS alarm system. And here we are putting the 5 most common technical issues, which we see in basically every building have more or less available these faults. Inaccurate sensors. If the sensor is showing unreliable numbers, then usually this is detached by the BMS as well. But sometimes it shows static values, or for example, CO2 sensor is showing unrealistic numbers or need calibration. We will detect these issues as well. Automation system ignoring schedules. It's very common, and it will cause additional consumption, and actually these faults could very easily offset our savings. So these are comments for the ventilation systems, which has their own internal controller. And so these systems can be controlled by the ventilation system own controller or through the BMS. The schedules are different, so they are not following the BMS schedule. And we're trying to find these kind of issues. And the failure to maintain set points, cascade logit failures, leaking cooling and heating valves, etc., etc. For example, leaking cooling and heating valves. Beside the valve position, we are checking the temperatures as well to detect such issues. So in practically, this fault detection part is very useful for the maintenance stuff. And for us, it's very important because these issues very easily could offset our savings or our impact. But yeah, let's move more to the console side. These 2 graphs are showing one office building. in Estonia, and our adjustment during almost during 11 months. So lots of small adjustments, lots of small set point adjustments. And left side is showing the reasons for the changes. Demand-based occupancy. So there are lots of occupancy-based changes. At the right side, what changes were made. So what we did, why we did, and what we did. And we want to be very explainable. So because still to be to offer a best service to the clients, and so yeah, it's very important to be transparent in that side. Proactive optimizations. So how we're doing. So firstly, while the building comes in, we need a human as well, because we have 300 buildings and we cannot fail. And so in the first steps, we need a human or engineer who select or who analyze how the building is working at the moment, and who select best appropriate models for the building. And after that, the building or like our AI assistant Jenny will do the work by herself. Then we have different models, for example, for the ventilation, what we can do, where is R, we are reading the points, where is W, we are writing. So we can control fans, temperatures, mixing boxes, for the cooling side, chiller temperatures, for the heating, different curves, and for the rooms, room temperature as well. So this gives a brief overview. Real example about the occupancy. As I told that usually the buildings are working on static conditions, ventilation working static condition. My background is also HVAC, and definitely I know that if there aren't VAV tampers, then the airflow does not change linearly with the pressure, because each terminal has its own resistance and control characteristics. So it's very important to understand the local system and how it works. But before R8, usually they work like static and timing, sometimes the full speed and half speed options available online. But what we are doing, we are firstly we add initial occupancy profile. It means 10 is like where the occupancy is maximum, and 0 where is unoccupied time. And based on that, we are controlling the ventilation fans, plus adding other inputs parameters like electricity price, etc. And for example, this example, if it is available, we are taking additional data sources. We are using additional data sources. For example, elevator data. New elevators have their own API, and where we get elevator data, we can adjust our original occupancy profile. So we can more act like the building is actually acting. And about the results, this is one case study what we did. So the blue shows calculated fans consumption while the building is using full speed, and before and after we're working our half speed. So 1 hour before, 1 hour after the regular occupied time half speed. While we added our initial occupancy profile, we got, it's orange, we got 20% of electricity fan saving, and while we had live data from elevators, we got in total 27% of saving for the ventilation fans. And in addition, heating and cooling coils as well, depending the season. And yeah, these are in our UI, users will see why we did something. For example, supplier temperature smart console. Usually, supplier temperature is controlled by linearly against the return air temperature, simple linear function. But we are using fuzzy console, which considers room status. It means while the room, we are at the room status for each room. If the room is cold, hot, or okay, it's neutral, it's green. And our goal is to achieve the situation where the most rooms are in a green status. And based on that, we are the fuzzy function will calculate supplier temperature. So in reality, it's a smoother and will help to achieve desired room temperatures. So it considers it's more related with indoor climate quality than the savings part, but it shows that we are how we are smarter way calculating accurate supply air temperature for ventilation unit. Okay, next example. For example, chiller. Most of the chillers are using a static supply water temperature setting. In most of the cases in Nordic countries, it's +7. And what we are doing, we are checking the room actual conditions and actual needs for the rooms, and for if the chiller is connected with the ventilation system, we are also checking the cooling coil valve status. And based on that, we are calculating or automatically necessary supply water temperature set point. And it's very common practice that approximately +1 degree will increase 2 to 4% of compressor efficiency. So this is just example before R8 and after R8, where the supply water temperature is changing. Usually we put like 7 to 12 degrees. Human will give the limits where the AI will make the changes in 24/7. So, and besides that, we are controlling free cooling setting. It helps to get savings from the tricolor fans, etc. And similar way, we are changing the heating graphs as well. So considering the real need.
Sorry, 3 minutes. 3 minutes time.
3 minutes time. Okay. Yeah. And okay, we'll go back to 3 minutes. Then a couple of more words about the cooling. And basically similar way for the heating. While there is additional need for heating, we are changing the curve, and while there is no need, we are lowering the curve to lower circulation losses. If it's a small building, the impact is not so visible, but if it's a big building where the lines are long, it will give a good savings. But as my presentation topic is about challenges and obstacles, so 2 slides about them as well. So most HVAC systems are not operating as designed, so they are designed in static conditions, except for the VIV system for ventilation, but mostly they are in static conditions, but they are not working. And during the time, the building are dynamically changing. The occupancy rate are changed, and so on and so on. So it's very beneficial to use more data for controlling the building automation or building service systems. Heating, ventilation, air conditioning systems, yes, I think significant. So it's a challenge for us how to get the most appropriate occupancy rates. Okay, sometimes we are using Google data for shopping malls. We can use sometimes elevator data, the doors data, and so on. So different data sources what are existing, and what we get, we are using them. And also, okay, significant difference in mindset, interior requirements, and HVAC solutions across regions. For example, in Japan, they like humid air. In Japan, the minimum is a lot of humidity is 30%. In Scandinavia, we are using humidifiers. Mostly only in hospitals and museums, where is actual need for them. So for office buildings, for shopping malls, we are not using so much humidifiers. Room controllers are very complicated. There are lots of different internal echo modes. So these are a huge challenge for us. Control. Okay, and also saving calculation, it's very complicated actually. Usually we are doing the whole building comparison, but as now we see, it's more necessary to do the more component level calculations to give more precisely our impact. This is just one example for the ventilation fans, where the orange line is before us and the red line is with us. And my last slide about obstacles. So I guess the main is different stakeholders. For example, facility manager. Many facility manager want to reduce complaints and lower energy cost. Technical manager, main KPIs, number of complaints, and tenant expectations. That's a real case. One office building, they wanted 24 degrees during the winter time and plus 22 in the summertime. So we have to convince tenant as well to get better results. And yeah, saving or impact calculation, technical issues, long troubleshooting times, and lack of sensors. So these are our main obstacles and challenges. So yeah, I think time is up.
Yes, thank you, Mikk. I think time is up, and I just remind for the audience participant, you can put your questions in the chat, and we at end of this webinar we go through the questions. But I now ask for the next speaker, Qian Wang, for the start for and his presentation.
Thanks, Risto. I will try to share my screen. 1 second. Let me know if you could see my screen.
Not yet.
It says I'm sharing the screen. Not yet?
No.
Okay.
Are you sharing the presentation or your desktop?
I'm sharing my presentation.
Try it again. It's not. Now it's coming.
Okay. Yeah.
Now it's okay. Okay, please.
Then I will continue. So thanks, Mikk, for the first presentation. It makes my life a little bit easier to continue on this. And also thank for the invite from Risto to do this presentation. And I'm from the Division of Building Technology and Design from KTH Royal Institute of Technology, Sweden. And today I want to briefly talk about our experiences when we work with, say, the transitions of the current building management systems. It's not only BMS, but also how it impacts the HVAC and insulation technologies that we have going through, and a few examples and exercises we have done to share with the audience. Yeah. So a little bit background that nowadays, I think building management systems are becoming increasingly important, not only because we have new product and new generation of BMS system and more data is required from stakeholders like property owners. They are trying to install new data, but also with the new EPDD and several requirements for renovations, we need to integrate much more system in the building, for example, different renewables. And also one challenge now for HVAC system is that when we discuss with, for example, industries, the scalabilities of the solutions is very important, because if we only have one solution for one building or one company, it's very difficult for them to have a, say, big impact to really change this business. That's the reason I think some of the challenges we wanted to prioritize. So first is how we can really make the BMS system becoming more scalable, and also how we can add certain, say, AIs to make sure it's easier to be done than before. Yeah, then a little bit experiences, maybe you also have experienced when we start to work with the current information systems, even though this is a very simple substations of Swedish residential buildings. You could see during the process of collecting data, we have conquered many challenges, because we have different information sources. You could see this includes, for example, control cards, the system diagram sometimes are drawn on PDF, sometimes it's drawn by some consultant, and then you have time series data, thread data, and sometimes they are tagged, sometimes they are not, sometimes they are stored in Excel file, and sometimes you need to have different access to the vendors who have provided different components, for example, the SCADA systems or web-port. So this means that the current situation for the data source is very scattered, and they are somehow locked into silos that is not easy to just put different models on it. We need to clean up this upstream process first. And second is that I think nowadays, at least in the research field, there are many existing approaches have been trying to solve this data problems. For example, there have been studies and projects working with semantic models, ontologies, and using, say, triplets, which are in the form of RDF. And there are also, I want to say that internationally speaking, there are open source ontology frameworks already established by different communities and different countries. For example, in Sweden, we have Real Asset Core, and now it's merged with BRIC, which is from the US. And on EU level, also we have Saraf. So this means that there are many sources and existing standards when it comes to how we could make, say, unified data models. But of course, these are developed by different people and different community and focus on different purposes. So what we should do with all this, then what our researchers have tried is to focus on not those very complicated buildings with a lot of data in the beginning. Instead, we tried with a simple exercise that is, say, rather old apartment buildings built in Stockholm, and it was built in 60s, 70s. So the system is not that complicated. You don't have many alarms jumping out all the time, but still it's not easy to do it, because you could see we need to even have field inspections to get all this data understood correctly. So there's a process to do this. And what we have tried is that how we should make this data being more, say, standardized, or how we can make them machine readable. So this is the reason we have used the semantic data models. That means how we create certain graphs and showing the relationships, but also mapping the data model into the same format, so potentially machine can read it. Because to be able to use AI or any kind of say, semi-automated approach, the first step is always that we need to make sure the data is machine readable. It's not meant for humans to read. So this was the first try. And then we start to naturally think about how we could make this process a little bit easier for the people to do it. Because if we look at the AI community, and there are several, say, potentials we can use AI to, say, simplify certain process from different data source into a unified data model. So what we have created is that what if we could convert this kind of data sources into a semantic data model that shows all the relationships, and this is so-called knowledge graph that I think maybe some of you have worked with. Then we add a layer of AI agent that is based on large language models, or LLM. Then simply we can do some data-driven prediction models. So all these kind of predictions or applications, we see it as the outputs of this approach. So when you have the model built and framework built, you can add many different optimizations or applications on top of it based on the need of the building. So this means that how we could do it, basically we have say 3 major aspects. One is LLM, because we want to use natural language to be able to perform human-like thinking. This means that you don't need to be the one to do the groundwork and dirty work. We try to use LLM to perform certain kind of processing. Then the semantic models. So because AI in general has a weakness, I think many of you know that, is that they are not very good with understanding the physics. This means that that's the reason we try to build this kind of semantic model layers to make sure the machine can understand the physical constraints. For example, the temperature for heating cannot be over 100 degrees or certain things like that. So you put certain physical relationships and indicators into the system. Then you have the function calling. This means that the LLM can use this agent to decide what, when, and how to use certain provided tools. For example, for your purposes, like FDD models or prediction models, time series, so whatever you want. Then this is a simple example or mock-up we have tried. It seems it's possible. For example, we create a virtual manager. So we did a simple exercise of say temperature predictions. So everything is done by the AI agent. We are not trying to interfere, and it's possible at least to be able to, say, perform certain tasks based on the raw data we throw in and the expected outcomes it generates. For example, this is just a simple application how you can predict your air temperature indoor from the FTX system, so ventilation system with heat recovery, which is very common in Swedish district heated buildings. Then we start to play a little bit with this exercise and try to see how this can help us creating semi-automated building simulations. That's another, say, use case we have been trying to collaborate and work on with our industry partners, because so far I think most of the building simulations has been done either by certain commercial softwares or use gray box modelings. Then what we are thinking is that, can AI agent automate certain process of this modeling, say, life cycle? Then if that can be done, this is quite interesting for both industries and say property owners, because this means that they can also try themselves to do certain things without large amount of physical data needed. So what we have built is a framework. Basically, you can see these are 3, say, layers. You have the middle layer that is a main LLM agent, but it cannot directly communicate with your data source, and the data need to be processed and cleaned up, as we said, as a machine readable format. This means that you combine databases, whatever you have, and your physical building system constraints or HVAC components, and the existing ontologies to be merged with information layer or knowledge graph. Then the LLM agent can call or call functions or recruit data for whatever you want. Then you should build a simulation agent that is not very complicated, but rather to be able to perform certain modeling works that you have asked to. Then, of course, you can build this that is very customized to whatever, say, applications you want. For example, for parameter optimization, you want to optimize certain ventilation system, valves. So the simulation agent need to be, say, customized to the use cases or applications you want to do. So can this work? Then we, of course, met certain, say, gaps when it comes to data model standards, because there are many libraries and trying to use LLMs and created semantics for this kind of large scale production, but still I think it's not fully achieved yet, because you could see there is say historical development when it comes to semantic modeling from 2014 to 2022. So it has been evolving, and I think one of the major challenging there is that it's very complex. It's not easy for industries or people without domain experts to just use it, and the process needs a lot of say try and errors. So this means that we need to simplify this, and depends on, for us working with HVAC industry, it's very crucial that we see a clear application values for this. That's the reason we try to further develop this more toward the industry applications. And then what we have done is that so far, based on our research project, we developed some open source services based on this kind of semantic model. They are simplified, so, and they are open source AI agent projects that you can clone or replicate or deploy this kind of work we have done. So basically, we are trying to build this with 3 layers. So first, we treat the building as an AI agent, even though it's not really possible yet, but this is a vision that how, so in the future, if building can run as an agent, so it can collect its own data, own semantics, and isolate it from each other. And then the design will be ontology grounded. So there will be a relationship of different data models to each other. Then, of course, the interesting part is that we want to build LLM agent on it. So this means that the machine can help us to run the whatever purposes you want, including, for example, modelings or computing, or even creating optimization strategies. So here is a QR code. You are welcome to scan it, and it's also on GitHub. And some interesting prototypes we have achieved. So we create this open source agent. Then we did it in Slack, and this means that we create a virtual colleague for us. So when we start to model it, there is actually a AI sitting beside us to work on the modeling together. Then it seems that it's working. For example, there are some questions we often ask them. Do you understand certain ontologies, or which data we will need? Or if you, for example, asking, I have the airflow and water energy meters. If I do this and that, how can you estimate the energy savings if we, say, for example, improve the air volumes? So, and it seems that it can perform this kind of energy optimization rather well. And this is fully done by the AI agent, not us, but we have prepared the background and also the models. So I think from the research point of view, of course, this is a simple application. A building involves many applications, but at least it shows promising future that this could be done in a way if we can start to work toward this. Yeah. And this work is done together with 2 other of my PhD students and colleagues. So you are very welcome to collaborate with us and give us feedbacks. So hopefully this kind of open source services, we can contribute to the development of the industries and the research field. Yeah, thank you.
Okay, thank you, Qian. You are really on time now that we have maybe after that have a lot of time for questions. So I still recommend for the audience to put questions in the chat. We can talk later. There is few of them available now, but please you can add it more. But let's move to the last presentation and then we have time to discuss. So I ask Davor if you share your screen, and floor is yours, or screen is yours.
Yeah. Hi everyone. So I'm Davor Stelja. I'm coming from Granlund, where I am serving as AI lead. And I'll talk about automating building design and consulting workflow, but I want to first start talking about how is AI used in MEP design and what are we doing to improve that. So first of all, currently, let's call it's mostly used in the productivity layer. So people are using, I don't know, stuff like ChatGPT to review their email, translate it, and things like that, do meeting summaries and so on. But it's very yeah, it's helping with office work and this stuff, but it's not directly applicable in the HVAC MEP design. Especially if you go to this kind of engineering layer like piping, routing, sizing, clash prediction, and these kind of things, they are definitely that is not done yet. AI is not much in that sense giving much, but we are trying to at least start from something in between, where you have in design or consulting project, there's a lot of this administrational work or let's say project work, where you need to document a change or you need to import some data from one source to another, and these kind of tasks can already be automated. Then coming from a literature, there was we checked how are LLMs used in MEP. So for example, in some source, they try just directly to use different AI models to do some kind of peak load calculations, and there was huge changes between the model, like how they predict it, and that kind of trying to say that don't use only an LLM model to do this. In a second article, there was about again, comparison if we just use a standalone LLM I think it was about structural analysis. But then if they use the same LLM and together with a tool like an MCP, which kind of was served as a connection to some validated solver, simulation engine or whatever, then the accuracy increased dramatically. So error was 400% in first case, and there was 1.5%, because LLMs are not meant for any kind of calculations and things like that. So that's why you need to use the tools, and with the tools you can then achieve pretty good work. Also, there was we were checking about how much these AI initiatives in company reach usage, and it says that 90% they don't reach impact, or they're not even used, and things like that. So these are the things that we are started with, and then we were thinking of what engineering AI actually has to be. So what are the main components that it has to be so you could kind of rely on it. And these are kind of summarization of 4 main properties. First is this integration, as I mentioned, integrating it to some proved software. So in case of energy simulation, you could integrate it to Energy Plus or something, or different kind of softwares. Then grounding, so you would ground it to either your old projects or some guideline standards, and so on, so that it kind of does the things how it should. And I have a note for that problem with the basic standard that we get says you shouldn't process this, you shouldn't use those standards for AI. So that's something that maybe standardization bodies should think about, how to how can we get a license that we can use it in AI. Then about the traceability. So in case AI has made a mistake, we want to know later where that we can track the whole process. So where did the problem happen? And that is really important. And finally, everything needs to be like with human in the loop. So if you just like input the data, get output, that won't work, because it's really you cannot trust it. And we want that our engineers who are experts, that they stay experts. So it's very important that during the process they are continuously involved. And here are some examples what we are developing. I won't go into too much details because that would be too much time, but just to give you idea what I mean. So one is first reading engineering building automation schematics, and hopefully in future also like generating it. So we produce a lot of these kind of diagrams, which is showing like air handling unit building automation, but they are manually drawn in CAD software, and it's very like error prone. And then parallel to that, our designers need to provide documentation, how this system works, describe it in words, what is the control logic, etc. These are the things that AI could do. So ideally, but like if you would send this as an image to AI, it is very buggy. Like at first it looks like it knows what is it talking about, but then the deeper you analyze it, you see that there's some problems. Sometimes pump is detected as fan, and vice versa, or something is missing, and then you send same drawing next day, it will give you a different answer. So pure AI is not that good in that, but it is in another way, it's at the same time really good because it understands the context. So if it sees a temperature sensor, it knows what temperature is, what is it measuring, unlike traditional machine learning, which is very narrow task. So combination of those two, if we would have like specialized tools and AI, that can really help. And what we are working on here is to turning these diagrams into knowledge graphs or some kind of other text-based schema that AI can then nicely work with to either do some quality checking or producing a description or checking the description against the image, and then hopefully in the future even generating, so we could just a human could describe what kind of system they want, and it will generate the whole drawing and the image and the text parallel to that. Then another thing what we are working on is we often get from different manufacturers, we get equipment description or specifications, and then we need to match it to our design, and this is done nowadays manually. You get PDF, and every manufacturer has a nice looking PDF but in completely different format. So those are the things that AI is really helpful. Ideally we wouldn't need this because all manufacturers would just send with API directly specs to our database, but we are not there yet. And then another thing is about classifying and tagging. It can be building automation data, what we are working on, but also other types of data that we have, standardizing it. That's a big work what we are trying to do, as that can be problematic. And that's why we as well, AI can do partially good work, but also it's important that the human is there in the process. Then, for example, we are trying to, some repetitive workflows, we are trying to make it in an agentic way so that depending on a project, different documentation would be analyzed, and it would the information would be structured. So if we have some report, it would extract the most important things that are needed for certain tasks to be done, like an, I don't know, LCA calculation or things like that. Then also from IFC models, how many certain components there are, and they can be named differently in different models and so on. These are the pretty annoying things, and we are trying to use AI in this matter as well. And then finally, we would like to merge this together, because like we could have like specific AI tools that do one thing. Let's say you extract from that manufacturer PDF specifications to some database. That's like one task, but then you maybe turn the some drawing into a knowledge graph so it can be used, but then it's not linked to the, for example, the documentation related to that and so on. So one important thing is to standardize the data and bring it to like break the silos, so we can kind of see different kind of data, and also operational data, what some others have here shown. It can be linked to the design and etc. And also it's very important during, for example, in design process, it can often last many years, that especially some complex project is done and many changes are being done. So AI could help us to do building projects more closer to like a software design project, where you would have like, I know probably everyone at least have heard of GitHub and this kind of Git process. So the same way you would have any new specs or anything that has changed. Let's say you in the beginning wanted to use district heating, then 2 years later they decide we will use heat pump. So all these kind of things is mentioned somewhere, either in email, document, on a meeting, and then you have like in the project, you have many documents that are still maybe referring to district heating. They don't have like, no one knows that they're, or you haven't changed the old file to say it's a heat pump. So then AI would do this for you, and you would have also the change log. You could go back if you've done any mistake or AI has done mistake, then you can revert back and maybe change the things and so on. So another, we were working on a white paper, which I'll show in a sec, but one thing that we wanted to emphasize is the human and AI collaboration. So how engineer and AI collaborate. And the main goal would be to eliminate certain types of load, but certain type protect. So you have basic, from cognitive load theory, you have 3 basic loads. One is extraneous load. So this is this kind of manual data entry or searching some data or some very like repetitive, boring tasks. So those are the tasks that AI would hopefully completely replace. Then there's the second, which is intrinsic load, where you have like maybe some calculation, like thinking of physical laws and things like that. There AI should work together with the human. So like make it break it into manageable components, and together with the human work to resolve the problem. But then the last one would be germane load, which is a kind of this thinking, creativity, and that part. And that's something that we would want that engineers, humans keep. So that's something that we definitely, AI shouldn't, let's say, it would be bad design of a software if we replace those things and then just like these mechanical repetitive tasks, we need to still do those. So engineering AI is bounded on 2 sides. On one, you have system side, where you need to integrate the data, standardize it, and do some kind of validation with some grounding with some rules, or either some calculation engine and so on. And second time you have human side, you need to like make sure that it frees your mind for judgment and creativity, but not erode it. So this is kind of where we want to be and how we want to build our solutions and our workflows in company that we do like that. And finally, I want to show you our white paper series. So we are Granlund is member of this First Q network, which is kind of a network of companies around Europe that are doing MEP design. And Granlund is the company from Finland. For example, from Sweden, there's Bengt Dahlgren and then there's several other countries. And we are working on in AI working group, we are working on white papers, and so far we have published 2. One is more general AI in MEP engineering. Second is this what I talked last, like human AI collaboration. And the third one, which we just finished yesterday, and it will be published soon, is about foundations needed for MEP AI, like data governance and AI-enabled design process. So you can download the first two ones from firstq.net, and then third one will be soon. Thanks.
Okay, thank you, Davor. Now we have heard 3 presentations and we have some questions here in the chat. And I think if I go through here, because this chat is not available, you cannot see it, but I can read it here. And maybe Mikk, you already answers here, but quickly response here that there is asked that how the system is able to analyze these sensors and replacement sensors or additional sensors and upgrading systems. So if you Mikk shortly describe.
I can comment it. So I think to comment it, it's our service. The answer is yes. But if I take only the Jenny will found faults, but actually she won't give too many recommendations yet. So it's partly manually or it's included in our service that we give recommendations as well. But the recommendations will come by the engineer still.
Okay, then there's other question for the Mikk also. It's more like a savings potential analyzing that if you have normally fixed 17, 12 chill water temperatures in chiller, and if you have this demand-based control, how much you can able to get energy savings there?
It depends a lot actually. It depends the climate, it depends the building and so on. But last summer we checked a couple of buildings, and while before us it was static +7, and while we are dynamically controlling it, we achieved average temperature like it could be like 9 or 10 degrees. So, but again, it depends a lot on the building. So I can say that maybe up to 10% of savings. And also we are trying to do a load shifting to cut extremely high electricity prices.
Yeah. Okay. Thank you. I think there's not other questions in the chat, but maybe I can ask for Qian. You talk about this ontology design and semantic models quite a lot and demand for that, but how you comment the existing situation for design practices and design documents? How far we are for that?
I think that part Davor has included several aspects in his presentation, and that when it comes to design part, actually we also did quite similar things when it comes to say extract information with different original format. For example, when you design it, you have certain wish from the buildings, or you have some drawings, and how you could extract that information into digital things, because design involves both new build and renovations. So when it comes to, so we so far has been very much focusing on the renovation part, because that's where the problem is. You need to design the systems based on whatever legacy system you have. So you really need to make sure this works as a system. And when it comes to new design, we did some exercise, but that's very much linked with, for example, BIM. So BIM models, because if you have nowadays, for example, at least in Sweden, if you work with like Bain Dahlgren or Skanska and NCC, you most probably for a new building now you have some sort of BIM. So this means that the spatial information is there, so you can build stuff on it. But for the renovation, it's a big challenge, because I think in one of the slides Davor presented, you have PDFs. Also, we have the same situation, and we need to go into computer vision to extract, like, which is heat exchanger, which is valve. Because when it comes to real operation, it's actually not as being operated as what has been designed initially. This means that when you design the renovation, you first need to make a detective work to make sure whatever you have there being designed is actually being operated. Then you design a new system on it. I don't know if I answered it, but
I think you answered, but maybe we can smoothly move to the Davor here. You can continue. If we now consider for new buildings, and Qian mentioned these BIM models, and how far we are with the BIM models and this semantic modeling, what you mentioned, that we can use in language models, AI tools, more efficient. How far we are?
Yeah, that's a good question. I think the new buildings, at least in Granlund, we started to use standardized models, and I think we have released for Finnish market, like publicly, the standardization, some guidelines and families and so on, that others can use. So that solves it much easier to use data than for AI. But in general, still most of the projects are either ongoing or previous, so which can be pretty messy, especially if you get it from a different stakeholders. They can have different formats. So like as I said, we are often now solving problem with AI that shouldn't actually needed to be solved. If, let's say, if someone produces a nice BIM model and then they deliver us a PDF, and then we need to distinguish which material was used somewhere from that, like using computer vision or something instead of like having. So there are problems like this, but so we kind of hack it by using AI to help us that. But there are other ways that it could be solved, and AI could be needed in half less cases, let's say.
And I want to say that also actually, BIM model, it itself is a semantic model. It's just it's only showing the spatial information, and there are a lot of other kind of say static data could be integrated into a part of it, like the material of the walls and the life cycle data of certain materials. This has been done a lot, but the challenge there is, as Davor said, you need to integrate all these BIM models with different BIM objects from different manufacturers. And then also the challenge is how you can integrate spatial semantics with time series semantics. That is, for example, from energy or whatever other data. Yeah.
I just Davor, you presented one control diagram where is a lot of control point and frequencies, but the thing, and after you have the PDF, and then you make for that with the AI tool for semantic model. Is also the big question why we don't first make a semantic model and then make a control diagram. Exactly. It's much more better way that. Why we are doing wrong way that we are doing process is not working well.
Yeah, I think we should do it. It should be like same as you are creating a software. You should maybe even by code or some other logical way, and then computer can do you a schematic. That's easy, like connecting symbols to each other, but you need to tell which symbols and where and how.
There is not questions in the chat, so I have a chance to discuss here and ask for the Mikk. You presented this building management interface, and over that you're making for your services, but How easy is to get this interface for the building management automation companies that you get the data in the right form and getting the data there? Is that difficult for your point of view?
Actually, to be honest, it's not so difficult. Most of the building management systems do have their APIs, and we have also our own APIs. For example, if they're using PACnet protocol, then we have our own PACnet API, and we can read in a PACnet network the data points. So it's not so difficult, but usually it's difficult to get design documents from the client. They are in a different format, and so if the, I don't know, in a shopping 20 years old shopping mall, they have had during that period plenty of reconstructions, and so it is difficult. But for getting the data points and data point addresses from the BMS system, it's not that difficult.
But the question is that if in the design scheme is not specified certain points in the automation system, you don't have those if you are using automation system as your interface.
Yeah, we are using automation system as our interface mostly. Sometimes, yeah, we have our own interface as well, and sometimes we made changes so that our engineer will understand and local maintenance will understand, but yeah, there could be differences. And so in that sense, we need engineer to do it manually, the connections.
Still no questions in the chat. I can continue with the Mikk. One thing you presented these fuzzy controls there, but they are not very easy to understand how they work in practice. That if you implement this kind of control strategy, how you test that they are working correctly?
Yeah, how we are doing? Yeah, lots of buildings. So firstly, we try it with our text database. Then we select a couple of buildings where they take one test building where we test it and manually checking does it work correctly. And still to be safe, we are giving the limits. For example, in that example, we gave the limits that the supply temperature could be between +19 till +21. So the fuzzy will work only between these limits. So but yeah, it depends on the logic what we are using. We are always testing it.
Okay, my last question is for the Davor. You have a lot of different concepts and thinking there, but one thing which you didn't present is some kind of customers or building owners or end users there in your slides, or did I miss something there? It's more like engineering practice. You don't got the interface for your end users or investors there, or do you have it there?
I mean, in all these that I'm showing, these are more for internal usage to improve the design or consulting process for our experts, like, as I said, standardizing data or putting it into like a proper format or doing some design work, but these are not meant for customers. Maybe at some point something like this could be, but yeah.
Okay, I cannot see any other comments or questions in the chat, but do any of your speakers, Qian or Davor or Mikk, you want to add something that we didn't mention and what is maybe now after the presentation you want to say?
And for us from KTH researchers, it will be very interesting. We could learn some experiences from industry partners, how this can actually be implemented in the say business world. And we are of course also happy to some sort of join any kind of white papers or community. We can share experiences because of course it's mostly like researchers and PC students working on it. So we want to have a strong say strong aspect from industry side, that how this can help with say your ongoing work and implementations later on. So yeah.
Yeah, we can be in contact.
Yeah.
Anything
That's
from
better.
Mikk? You have something what you didn't say or want to say? Some wisdoms for the audience now.
I think more or less I go through what I wanted to say, but yeah, in reality, yeah, we're using more like hybrid models, so we cannot trust fully AI. It's not so reliable. We are also using in our office work different LLM to do our office work. And beside that, we have lots of internal tools to test and so on. And also we need humans as well, engineers who are communicating with the client, who understands how the building should work.
Okay, Davor, anything add?
Yeah, I think it's what I already mentioned, but a lot is about cleaning up data and standardizing data. And what I saw in different MEP companies across Europe, they have the same problems, and that's really messy. And I think that's something that you should start first, because then it will be easier to integrate with AI workflows much easier than otherwise. But also AI can be used to help that, to standardize the data and help you organize things better.
Okay, I think I cannot see any other questions or comment in the chat, and I would like to thank all the speakers and all the listeners there, and also a great thanks for the Siru Lönnqvist, who practical arranged many things for SCANVAC point of view, and I'm quite sure that we will have this topic, maybe webinar in the next year. I think there's a lot of progress happening now out there, and maybe there is the need to have other ones. So. Okay, thank you for everybody. And then I want, if all the speakers, you stay a couple of minutes here, we can discuss after that here. But audience, thank you for listening, and we see maybe the next webinar a little bit later this year. Thanks.
All right, thank you.